Welcome to That One STEM podcast. I'm your host, Vihan, and today we're thrilled to host an extraordinary mind in the field of space science. Dr. Martin Elvis is a distinguished astrophysicist with a remarkable journey that spans over 3 decades in asteroid research and exploration. He started his career with a passion for understanding the mysteries of the cosmos, diving deeper into the world of deep space bodies such as black holes and doing groundbreaking research in that field. But it was his visionary thinking that drew him towards asteroid mining, a field in its infancy when he began, yet one that he helped to grow with his contributions and bring into the global spotlight. Dr. Elvis's groundbreaking research has paved the way for how we think about space resources, sustainability, and the potential for mining asteroids to advance human civilization. His work not only redefines what's possible, but also inspires a new generation of thinkers to view space as a frontier for both exploration and preservation. Join us as we explore his incredible journey in astronomy and astrophysics and gain insights into the future of asteroid mining. Dr. Elvis, thank you for being on the show.
Yeah, pleasure.
I was just curious, you've had a very extensive experience in the field of astronomy. So I was just wondering, for the listeners, what would you say is like the main value that you've held on throughout your life and throughout your career?
Well, what I always wanted to do was to find things out, to discover stuff. And so I lucked into a field which was really young and ready to burst open and with great things. So that was great fun. And then trying to understand what we've discovered, I was always guided, I think, by aesthetics, that it had to be a pretty solution. There had to be a nice answer. And so I've done a couple of things where I think I found a nice answer that other people hadn't. That's been a lot of fun.
Wow, that sounds wonderful, sir. The second question that I had was, you've done significant research in the field of astronomy and into the research of deep space bodies such as black holes. So what would you say are your main takeaways from this field, both technical and general?
Well, when we started, we only thought, well, maybe they're giant black holes. So it was like very weird and out there and extreme to say there were giant black holes in the centers of every galaxy. Watching that change from like, that's a bit too exciting and dangerous to say, but could be, to now it's like, duh, of course there's a giant black hole in the center of the Milky Way, right? We've seen it, we've imaged it. It does exactly what Einstein said it would. And that's a wonderful change. And now it's kind of ho-hum, but to me it's still kind of amazing.
What would you say was the most interesting thing you researched or discovered?
Oh, well, I'm most famous, like people have cited my papers most, for just mapping out the emission of quasars across the entire electromagnetic spectrum, from normal light, infrared light, X-ray light, even radio. And the odd thing about it is that these black holes, which we call quasars, when we can see them shining brightly because gas is falling down onto them and getting very hot, is that unlike stars, they emit almost the same amount of power at every wavelength band. Every octave of the spectrum has more or less the same amount of power coming out. Stars are totally different. Stars are like single temperature. And that means they have a peak. For the sun, it's a 6,000 degree temperature as its surface. And so you see a curve that matches that beautifully. And it peaks in the optical band, which is where we can see not with our eyes. And so it's very, very different. And why is it very different? Good question. But we have clues. That's what I'm known for. What I actually enjoyed most was realizing that the structure of quasars could be explained quite simply with a particular structure. And it explained hundreds, I think, or at least dozens of peculiar facts that had seemed to be kind of random and not part of a single big picture. And I think by putting this suggestion forwards about what a quasar actually looks like, and that they all look the same, I think that moved people's ideas about how quasars work quite usefully. And it was something that kept me up at night. I mean, I woke up in the middle of the night thinking about this and going, but in that case, even the flying region could be part of, which, of course, meaningless jargon to you folks. But to me, it was something I'd been living with. And that the trick is to learn that I had to learn hundreds, probably a few thousand different details in order for them to sort of eventually form into a single coherent thing in my head, right? And it went step by step. Well, I suppose it could be a wind coming off the accretion disk. But then, but it could bend, and that would explain why, yeah, right? That kind of, it just kept going for months. And it was complete obsession. And so when I came out with that and published it, I was feeling very scared because I thought people would pounce on it. And instead people went, it's quite nice. Because I wanted them to say, you're a genius, it's the best thing since sliced bread. But they didn't do that. They just said, hey, that's a good idea.
Following on the topic of your research into deep space bodies, what made you interested in quasars and black holes? And
well, I was starting, astronomy was remarkably primitive compared with today. Luckily, there were people who studied stars, and that seemed just inherently very boring to me because we basically understood stars. They emit this single temperature spectrum and otherwise it's details, and we understood how they worked. I wanted something where we didn't understand anything, and that the answer was probably pretty amazing. And quasars turned out to be that. Of course, I didn't actually know I was going to study them straight away. They were at the back of my mind. But I was working on a new instrument which was scanning the sky and making a survey of the whole sky in X-rays. I thought, well, these quasars are energetic things. They're bound to show up in X-rays. And to my great piece of luck, a great stroke of luck for me, they did. And we established that the quasars, which we called at the time safer galaxies, details, did turn out to be strong X-ray sources. And that should have been a surprise, except I didn't know the literature well enough. I didn't know previous research because it was a new paper that had just come out and has been one of the most used papers, cited papers in all of astronomy, saying, well, the temperature of these quasars should be only about 50,000 degrees, maybe 100,000 degrees. That's still 10 times hotter than the sun, but that's not hot enough to make X-rays. So I should have been surprised and not even bothered to look because we knew that they wouldn't be hot enough. Instead, I was ignorant enough that I looked. And that turned out to be a really great thing. My whole thesis, PhD thesis, it can be said as Cepheid galaxies, quasars, are X-ray sources, and they vary rapidly. In a day, they can double in how bright they are. And that turned out to be important because it was the first proof that we were looking at something very, very small, less than the size of the solar system, and yet it poured out enormous amounts of energy. And so it became very hard to explain it with anything except a black hole.
Just for the sake of the audience, what would you say is a quasar?
Yes. Okay. What people keep finding that there were these bright things in the sky that were not stars because, like I said, they have radiation spanning an enormous amount of the spectrum, doesn't look at all like a star. At first, people say, oh, look, they have ultraviolet excesses. And then they looked at the other end of the spectrum and said, oh, they also have infrared excesses. And they're just totally excessive things. They're all over the place. Meaning compared with the star, yes, because the star is like this, a tiny, narrow distribution. Quasars emit all over the place. They're very, very powerful. They're so powerful that you can see them out to the edge of the universe that we can reach so far, back to the first few 100 million years of the age of the universe, which is, that sounds like a long time, but it's actually not very long compared with the age of the universe. Anyway, so, what we now understand is that they're powered by gas falling down onto the black hole. And as they come down, streaming down at high speed down the gravitational well of the black hole, which of course is intense, they hit each other and make very hot gas, and that radiates intensively. And then the details of how that happens, is it through a disk? Is it through clouds? That takes a lot of work. But the basic idea is energy is released because gas is falling into the black hole potential well. Once it goes into the black hole, past the event horizon, it doesn't do anything, not to us.
I'd just like to ask, a major event in your career was from when you went like with the research of, deep space bodies and astronomy and switched to the field of asteroid mining and planetary resources. So could you explain why you made that sudden switch?
Yes. There's a joke version, which is quasar means quasi-stellar object, and an asteroid means almost a star. So obviously they're the same thing, but in fact, they're totally not. Because a quasar is, like I said, in distant galaxies out to the edge of the universe, and an asteroid is just a small rock in our solar system, the leftover floor sweepings from the formation of our solar system, just a few old rocks, which for a long time I didn't think was very interesting at all. We were too busy looking into the far distant to even focus on something in our solar system. And I think most astronomers also had the same idea that anything in our solar system is just too small and uninteresting. That's completely wrong, we now know, but that was the fashion at the time. That's where we were not making progress much with the solar system, making huge progress elsewhere. But what happened was I'd been blessed by having 2 generations of instruments that could map out what quasars looked like across the spectrum, better and better ones. So the first one was with the Einstein Observatory in X-rays, the International Ultraviolet Observatory in the UV, and the infrared astronomy satellite in the infrared. I used that to create that first paper that I said made me well cited by my peers. Then there was a second generation, which is called the Great Observatories, and that's the Chandra X-ray Observatory, the Hubble Space Telescope, and the Spitzer Space Telescope. And the 3 of them were well matched in what they could do. And again, but now we're talking 100 times more powerful than the first generation. So you want to keep that going. And yes, we have done that in the band, more or less, between what Hubble and the Spitzer Infrared Space Telescope could do. And that's called the James Webb Space Telescope. And the problem is there's nothing matching it at shorter or longer wavelengths. So the ultraviolet and the X-rays in particular have been left behind, and it's very hard to do the kind of science that I think is demanded in the 21st century of looking at the whole spectrum. Because if you miss out a piece of the spectrum, you really miss an enormous amount of the story. It's like looking at a black and white photograph instead of a color photograph. It's just silly. So the problem is, James Webb Space Telescope costs $10 billion, and we can't afford 3 of them. So how are we going to make it cheaper? Well, I thought, what's the American solution, right? The American solution is always capitalism. And one thing capitalism is good at is bringing the costs down. And if you have competition, at least, right? It doesn't work with monopoly. So if we could get commercial interested in space and doing things in space, it would bring the price down. And the answer is that, yes, that correct, Martin, that has been the way, because SpaceX and now others are doing that very dramatically. But when I first started on this, there was very distant prospect. But I thought if we could find resources in space that were worth mining, then that would get people interested. And so I started to look at asteroids, because they're, in fact, full of resources. And also the techniques used to study them are just the same ones I use to study quasars. They're both just dots of light in the sky. The difference is quasars stay where they are and asteroids move because they're nearby and in an orbit around the sun. So that went quite well. And I started trying to work out, well, how many asteroids are there that are worth mining? And of the ones known at the time, the answer was about 10, meaning 10 worth $1 billion or more. And what venture capitalist would get out of bed for less than $1 billion, really? Come on.
Yeah.
So that wasn't promising, but the answer is now that we've had another 10 years of surveys, now that we're able to launch bigger rockets, or soon will be, with tests of Blue Origin's New Glenn, and of course, most impressively, Starship coming up, we're probably going to be able to reach hundreds of asteroids from which you could mine $1 billion worth of material. And There were a couple of companies that started asteroid mining as an idea just after I gave my first talk on the topic. I had no idea they were doing it. And then suddenly, instead of being a prophet in the land, I suddenly became also ran. But both of those companies went bankrupt or actually got bought out and are not doing asteroid mining anymore. But there's a new one called Asteroid that is planning to send its first spacecraft prospecting an asteroid fairly soon. They've just had permission to launch it.
So, Dr. Elvis, as a advocate and an expert in the field of asteroid mining, what would you say are the main arguments towards asteroid mining? Like, why couldn't we continue mining here on Earth instead of mining in space?
Well, it depends if we going to need more and more resources or not. And with our current economic system, it's set up to grow endlessly. And for that, then you're soon going to need the resources of the solar system and not just those of the Earth. That may not be a sustainable model, but we'll see. The immediate interest is maybe we can supply new commercial space stations with more water and materials to build in space, like iron to build out. You need water in space for survival, for life support, for making oxygen out of the hydrogen oxygen of the water, for growing crops. You can't take a salad to orbit because it would be the very most expensive salad you ever had, and so on. You also need it for hygiene, and while the early space tourists might be happy to show their tough guys or something, tough folk using the ISS toilets and no showers and all the rest of it, that's going to wear off pretty soon, I think, among many multi-billion millionaires. And they'll want at least the comforts of a 5-star hotel, which would surely include a shower and a decent toilet that worked, right? So most of us would prefer that. So I think that there's going to be a demand for a lot more water in space. And it turns out the amount of energy you need to bring water from an asteroid or some asteroid is a lot less than the energy you need to launch it from the ground. So in terms of physics, the asteroids are the obvious place to go. In terms of economics, maybe not, right? Because there's an irony in that SpaceX Starship may bring down the cost of launching things to orbit by 10 times, which means you can launch a good-sized asteroid mine robot and get a return on investment more quickly than you would otherwise. But of course, at the same time, it's 10 times cheaper just to fill it up with water and send the water there. And that's a much quicker solution. So which one will win in the end is not a matter of physics. It's a matter of economics. And we don't know the answer to that. And we won't know for a while, for a long time, quite a long time.
So, in your opinion, as an expert in this field, how well poised would you say are we to send that first asteroid mission? And how long do you expect us to wait to see that first asteroid mission to be sent into space?
I would have said we're going to know an enormous amount more in 10 years because there are 2 surveys starting very soon. One this year from a mountaintop in Chile. Forgotten the name of the telescope. The survey is called Large Scale Survey of Space and Time. It's going to photograph the entire visible sky from Chile, not the northern hemisphere, but the southern hemisphere. Every 3 nights they will get an image, and they'll take pairs of images or even triplets of images so they can see asteroids moving. And so they'll be cataloging very large numbers of asteroids over the 10-year mission. And then a little later, NASA is launching a thing called the Near-Earth Object Surveyor, which is deliberately working in the infrared, where these asteroids, instead of being dark because they don't reflect much sunlight, they're very bright because that absorbed sunlight heats up the rock and it makes it glow and in infrared light. And so they're choosing the wavelength to look at it to be where it's brightest. That's a very clever idea. Amy Mainzer at University of Arizona, really the mastermind behind this. And that will start working in 2027, probably. and last 5 years, and they will also find probably not millions, certainly millions of asteroids. Their main goal is to find ones that might hit the Earth and destroy humanity, which is it's a good idea. We wouldn't want to be wiped out like the dinosaurs. But at the same time, they'll find huge amounts of asteroids with good resources that could be used in space for furthering exploration of Mars and beyond, or could be used as resources for people for an in-space economy, or for people in space doing whatever. So I think that's what I would have said. But now the Astroforge is already forging ahead by sending a mission to an asteroid. Maybe I was too pessimistic. It's a mystery of the market, because you never know when to jump in and do that new thing. And the first guys 10 years ago were too early. You can't be too late, because then you've missed out. Maybe Astroforge have found the right moment. We'll see.
Following up on the point about how you said that we're currently looking into the solar system, trying to see asteroids that are hazardous to us, would you say that, like, within the century or so, we're at risk of having a catastrophic asteroid impact, like as in popularized in pop culture?
We had one in 2013 when Chelyabinsk, the Russian city, had casualties due to flying glass because of the asteroid impact in the atmosphere high up at a grazing angle, and it sent out shockwaves that broke thousands of windows. Had that come in at a slightly steeper angle, it might well have hit the ground and made essentially the equivalent of a nuclear explosion. Just the amount of energy involved, right? And that could have destroyed the city. It's actually very hard to calculate what would happen in detail. So could that happen again? Those things happen roughly once a century, once or twice maybe, but it's statistical, which means that at any time it could happen. It's not on a nice regular every time for another asteroid, no, it's just like kind of random. And it could happen anytime. So it's smart if we find as many as possible, and then we can start trying to deflect them, like the DART mission showed when we punched a little moon of an asteroid with the biggest spacecraft we could, moving as fast as we could, and saw what happened. Did we change its orbit? And the answer was yes, by 10 times more than we'd expected. So it can be done to save ourselves from being hit by asteroids. Of course, the big one is if something a kilometer across came after us, which is the kind of scale that kills off dinosaurs and would kill us off too. And we found 90-something% of those. There's estimated to be 1,000 of them. We found 900 and something. So we're doing well, and none of those are a threat right now. But the 2 new surveys should fill in, we hope, all the rest. Let's hope it's all of the rest, because it only takes one to destroy humanity. So it's very much worth trying to do that, I think, regardless of any kind of commercial consideration or anything else.
Moving back on the tangent about asteroid mining and exploiting asteroids for their resources, what would you say is the biggest challenge facing the asteroid mining industry and facing companies like Astroforge?
They want to mine precious metals from iron-rich asteroids. And when we say iron-rich, it could be a solid chunk of iron, not just a few percent. There are meteorites. If you go to a science museum, you'll often find an iron meteorite sliced in half, and you can polish the surface. It's like a mirror. It's that pure an iron. So they're looking for that kind of asteroid from which the meteorites come. And then they're looking for ones which are rich in platinum and related metals. That would be easy, but takes them a lot of prospecting. And the biggest problem is even the richest ones only have a few grams per ton of precious metals. So that's a little bit of a extraction problem. How do you go from a few grams per ton to having a solid lump of platinum or palladium or whatever that you can take home and send home and sell? So I don't know how they're going to do that. I'm not by no means an expert on that kind of mining technology. I'm sure they've looked at it. They were planning to test it on orbit, but they had a problem. But it's quite a triumph if they can do that. Then I think they've overcome one of the toughest hurdles.
As the final question to end this off, asteroid mining is a very lucrative and promising industry, but how would you forecast the balance between commercial interests in space as well as geopolitical interests between countries?
Yeah, we don't know it's lucrative yet, by the way, but it might be, and we should think about what happens if it is. And that's actually a real question, because one of the other things I did was look at the distribution of asteroid resources, and they are concentrated in not just in a small number of asteroids, but it's most of them are the biggest asteroid most of the resources are in the single biggest asteroid of its type, whatever type you're looking for, be it iron rich or platinum rich or water rich or whatever. Which means it's very easy to get a monopoly on. If you found this asteroid, you're mining away at it, you can probably put other people off from landing on it. And if they do try to land on it, then you've got a real tense situation, because it becomes who can gobble it up fastest, and that's prone to producing conflict, and we want to avoid that. So there has to be some kind of international governance of these rights to mine things. And that's going to take an awful lot of negotiation. And one of the factors we'd like to include in that is, well, what other uses for this asteroid might there be, right? Is it a good one to turn into Mars to Earth shuttle, which can be one arm? So you can move asteroids onto an orbit which goes past the Earth, and then a while later goes past Mars, and then comes back and goes past Earth, and then goes to Mars. And why bother with an asteroid to do that? Because you can burrow inside it and have huge amounts of rot between you and the deadly radiation of space, and that can protect you. So it could be a way of getting to Mars without getting cancer, which, seems like a good idea if you want to go to Mars. That would be the better way to do it. Or can you use an asteroid for science? What value does it have for science? And there's a lot of history of the solar system encoded in some of these asteroids. Which ones would you protect? Which ones would you set aside and say, no, you can't mine these are too important? And then there's the aesthetics again. The largest asteroid is Ceres or Charis, and it's very largely water. We now know it's the only spherical asteroid. So under its own gravity, it's become round. It's unique. And yet it's probably a great source of water for a long time. So should people be allowed to mine it, or should it be preserved as a kind of solar system national park equivalent, right? So there are arguments, which I guess we don't have time to go into, that we should set aside the great majority of the solar system as wilderness, not to be exploited economically. We paper with myself and Tony Milligan, and my ethics colleague, suggests 7/8 should be set aside. It's a starting point. So it's going to be a lot of work to go from pointing out the problem to getting a solution. I'm hopeful that the first place this will happen is on the moon, because it's a more urgent problem, and the same difficulties apply. That the competing uses for a small number of small locations is something that we want to avoid conflict on. So I hope science can help make that happen.
Well, Dr. Elvis, thank you so much for being on our show and taking time out of your busy schedule for our listeners, to learn about your experiences in in astronomy and in asteroid mining.
A pleasure, Vito. Glad to do it.
Thank you for listening in on today's episode. If you have any queries, comments, or questions, feel free to reach out to us in the email listed in the show notes. And we hope you learned a little bit more about the field of astronomy and planetary resource from this interview, and we hope you have a great day ahead of yourselves. This is your host, Vihan, signing off.